In first year chemistry, we spend a time talking about the development of the atomic theory from very early models like John Dalton and his identical rigid spheres through the discovery of the electron by J.J. Thomson and the plum pudding model, and then the Rutherford gold foil experiment, which allows Ernest Rutherford to discover and postulate the existence of the nucleus. And in AP chemistry, we're going to focus on two models of the atom. One, of course, the current quantum mechanic model of the atom, where we use a great deal of math and modeling to understand what's going on inside the atom. And occasionally, it's handy to use the simpler model from Niels Bohr, the Bohr model of the atom. So let's talk a little about the Bohr model, which came before the quantum mechanical model, and what it does well and what it does not do well. Bohr is investigating and trying to understand a very important question. In the Rutherford model of the atom, you have a positively charged nucleus with electrons out spinning around the nucleus. But according to classical physics, this atom is unstable. Accelerating charged particles should consistently lose energy and the atom should collapse. So Bohr is trying to answer the question, why not? Why don't the electrons fall into the nucleus? So he states that the electrons are moving like planets around the sun. They're in circular orbits at different distances, and a certain amount of energy separates level 1 from level 2 and level 2 from level 3. So the Bohr model looks kind of like this. We have a small positively charged nucleus. Thank you, Rutherford. We have the electrons out here, but instead of being at any distance, they are in particular orbits at different energy levels. Bohr postulates that this energy is a fixed number related to that orbit or shell, that electrons cannot be in between those shells. So there's no floor 2.5, it's either 1 or 2. The higher the energy level, the farther it is away from the nucleus. And Bohr postulates something here to explain the relative inertness of noble gases and ions, that an atom with the maximum amount of electrons in the outermost orbital energy level is low energy or stable and unreactive. One of the big pieces of information that Bohr uses to develop his model is the emission spectra, the light that is emitted from excited atoms of an element. And the first thing he looked at was the simplest emission spectra. We've seen this in first year, and we'll most likely look at it again in this year. The emission spectra of hydrogen gas. And we can almost always see the red and the blue light. Those are in the visible spectra. And then oftentimes we'll see, if it's dark enough, you can see the purple, but you generally will not see this because this is down in the UV range where our eyes are not able to pick it up. And different elements have a distinct, unique line spectrum involved. You can see here's helium, which has quite a few more lines than hydrogen, and carbon, which is even more complex. And this is in fact one way that people would determine whether they had found a unique, different new element, or whether they had simply isolated something that was old. If you looked at the line spectrum and it matched a known element, then you knew that was what you actually had. Now, the Bohr model of the atom does a lot of things very well. It helps to explain periodic law. When a shell or energy level is full, elements will not gain or lose electrons. And so halogens are so reactive because they're only one step away from that complete outer orbital. Alkali metals are so reactive because they're only one electron away from that outermost orbital. And this connects to some very old ideas about reactivity and valence from the 1800s. But obviously there are issues with the Bohr model of the atom because it's not the model of the atom we're still using today. So let's look at the math that Bohr is doing. Okay. We have the different energy levels and they are discrete. The transition energies are perfect. They are exact, specific amounts of energy that correspond to the different transitions. This is the Balmer series, and this is the one that you will generally actually be able to see. These are those 4 lines on the spectra before. The atom kind of looks like an energy well. The lowest energy state is the most negative, and then it gets less negative as you go up. So this is because Bohr defines 0 as a free electron floating in space with no attraction to the nucleus. Well, we know logically that in order for an atom to stay together, it must be energetically favorable for an atom to exist because they are certainly all around us. So if we define an electron by itself as 0, and an electron in an atom must have less energy because that's how we get nature to agree to hang on to atoms. A good analogy for the Bohr atom is a ladder. Further away from the nucleus means more energy, and there's no in between. Just like you can't stop at rung 2.5, you can't have an electron at state 2.5. Just like you can only stand on a rung of the ladder, electrons can only be in those specific energy levels. Unlike a ladder, though, if you look at the hydrogen atom, or any atom really, the energy levels get closer together as you go higher out. So each one of these energy levels corresponds to a different distance from the nucleus or orbital radius. Since we're then talking about traveling a different distance, that does mean we're going to have a different velocity. And eventually we come to understand that that means a different wave function and a different energy. And those levels are eventually going to be described by the quantum number n. What energy level are we in? So if I just needed to calculate the energy level of a specific electron, there is, of course, an equation for that. And it is very simple. I've got it here in electron volts because that's a very common measure that you'll see in dealing with these very, very, very small amounts of energy. If I just need the energy of a level, I just take minus 13.6 and divide it by that energy level squared. So for n equals 1, it's 13.6 because 13.6 divided by 1 is 13.6. If I do n equals 2, I'll take that negative 13.6 and divide it by 2 squared. So I'd be dividing it by 4. And that's great, but we remember that these emission spectra that we see are actually transitions between energy levels. So it's usually more useful to use what's called the Rydberg equation to calculate the energy that I see between 2 energy levels, the transition here. And that's this bottom equation, that's the Rydberg equation. R is 2.18 times 10 to the negative 18th joules. And the delta here is 1 over final minus initial, and you do notice that's squared. So you can basically see where this is coming from. It's very similar to this. The R is different because this is in joules and this is in electron volts. And you'll see R, the Rydberg constant, in multiple different units all over the place. So what are the problems with the Bohr model of the atom? Well, molecules have a shape. They have very predictable shapes. And there's no real explanation for that Bohr just has electrons in random in these different orbits and they're all around the nucleus. So why would they be at particular given angles like we see in experiments with molecules? Really, honestly, Bohr doesn't explain why. He just says they're out there orbiting at these energy levels and they don't collapse because they can't collapse because they're at these energy levels. Um, but then there's a huge problem. The mathematics work beautifully for any single electron system. Hydrogen, a helium plus ion, a lithium 2 plus ion, it's beautiful. But the minute I add more than one electron, the math stops behaving. So obviously, we haven't come to a complete understanding of the electron using the Bohr model. Where it is very useful for us as chemists today is this idea of the energy shell and the transitions between higher to lower energy shells emitting a certain amount of energy and the absorption of certain wavelengths of energy causing electrons to move from lower shells to higher shells. For our purposes, we don't need to go into huge amounts of quantum mechanical detail and what's going on with absorption and emission spectra. But so we can use these simple shells of the Bohr model to help us out.